Okay, hi everybody, and I hope you're having a good spring break, those of you who are doing this on time. I'm going to try to go through this video rather quickly. We're going to start with angles of polygons, and before we actually start talking about angles of polygons, we need to review very quickly some of the vocabulary for polygons that we've already talked about earlier in the year. But because we've already done it, I'm going to go through this rather quickly. So if you need some additional help with that, I would suggest watching through the video a couple of times or pausing it to try to absorb everything that the slides are saying. All right, we're moving on. Okay, a polygon is a plane figure formed by at least 3 segments called sides. Okay, let me grab my magic pen, which is somewhere. There it is. Okay. Called by at least 3 segments called sides, such that no 2 sides with a common endpoint, called vertices, are collinear, and each side intersects exactly 2 other sides. Okay, it's actually quite simple. You have a bunch of segments that join together. Okay, they don't have to all be the same length. They don't have to all have the same angles. Okay, as we know, each one of these sides here is a side, and each time we have 2 sides that meet, that's a vertex. Okay? They can't be collinear, meaning you can't have 2 segments that look like this. One segment, a second segment, because that's just one line. They have to have an angle between them. And you cannot have something like this, because that right over here will intersect more than 2 sides will intersect at a common vertex. Okay? Can you explain why this figure is not a polygon drawn below? Well, there's actually a couple of reasons. This line right here, being there, means that A and C both have more than 2 sides at a vertex, which is not allowed. And also, if you notice real closely, DA is actually curved a little bit, so it's not actually a line segment. Okay, let's see if I got that right. Yay, I'm smart. All right, let's go on. Types of polygons. We've talked about a bunch of these, but you will need to know all of these words. 3, 4, 5, 6, 7, 8, 9 sides and 10 sides have special names that I will expect you to know. After that, it's less important, but triangle. Let's see. Triangle. Quadrilateral. Pentagon. Hexagon, heptagon, octagon, nonagon, decagon. I expect you to know all of those. And then I want you to notice what happens on some of them after we get... That's not supposed to happen. After we get past 10, you can start calling them just by the number of sides. An 11gon would be a polygon that has 11 sides. Okay? And you can see the generalized form of this right here. An n-gon is a polygon that has an n number of sides. Okay? A dodecagon for 12 sides is there. It has some special properties to it, but you don't really need to know about that. Okay, let's see what's next. We talked about convex and concave again. Convex just means that it looks like a normal polygon. If you extend all of these lines, you will not hit any points that are supposed to be inside the polygon, like you might if you had, say, this figure. Okay? If you extended this line right here, notice right over here you're starting to hit points that are inside the polygon. Okay? That's all you need to know. Convex is the kind of polygons we really want to be talking about for this chapter. Concave, the exact opposite. If you extend this line right here, right over here, you will hit points inside the polygon. You don't really want that for a lot of the theorems we're going to talk about. Figure below is a polygon, true or false? Well, we've already talked about this exact same one. Because there are multiple intersections right there, it is not going to be a polygon. However, this one would be. Notice they do not touch. As long as they don't touch, you have a polygon. Okay. Figure below is a polygon, true or false? Well, this one doesn't break any rules. Okay? We have, for every vertex, we have 2 lines meeting. Okay? And it is a closed figure. They are all line segments. And even though it is not convex, notice I can draw that, okay, it is still a polygon. Identify the polygon. Well, this one is awfully easy, so let's just do it quickly. We've got 1 side, 2 sides, 3 sides, 4 sides, 5 sides, 6 sides. What do you know? That's a hexagon. Yay! Okay. Is the polygon convex or concave? The question is, can you extend a line for concave, for it to be concave, can you extend a line such that a point on that line is inside the polygon? Right there, I just drew it, so it has to be concave. Is a polygon convex or concave? This one, I can extend that one. Nope, don't have any points inside. I can extend that one, don't hit any points inside. I can extend that one, don't hit any points inside the polygon, don't hit any points inside the polygon. For every line that is true, this is a convex polygon. One way you might want to think about to remember it is concave polygons look weirder than convex polygons most of the time. Okay. A polygon is equilateral. You must know that word. It means equal sides if all its sides are congruent. A polygon is equiangular, equal angles, if all of its angles are congruent. And then regular just means that it is both equilateral and equiangular. We've done this before. You just need to remember that. Okay? Okay, now we're going to get into the new stuff. I have a bunch of figures drawn up here. They are all convex polygons, which are the ones we're going to be working with. You've got your regular triangle. Then that's over here. Okay? Then you come over here, you get your quadrilateral, your pentagon, and your hexagon. Okay? What I have drawn in each one of them, or what has been drawn in each one of them, is a diagonal. And it is only a diagonal from one point. So what we're doing here, to be able to develop the first theorem, is we start at a vertex, and we are going to draw all of the diagonals possible from that single vertex. Now a diagonal goes from a vertex to another vertex that is not adjacent to it. This one right over here would be adjacent, and this one would be adjacent to this point right here. So when I start from this point there, the only diagonal I can draw is the one that's right here. Okay? Because the other two would make adjacent lines, and those are just sides. So that is a diagonal. And then we are going to do the same thing with our pentagon. Draw all of the diagonals from a single point, right there, and right there. And from here, we're going to do the same thing. Right there, right there, right there. Now, some of you might be wondering, why in the world are we doing this? Well, the question down here, what do you notice about the regions created by the diagonals? If you think about it, all of the regions are triangular. Okay? So we've got, I'm going to switch to purple. We've got this one right here, and this one right here, triangles. This one right here, this one right here, this one right here, triangles. Same thing for the hexagon. All of the when we draw all our diagonals in from a single point, we have a whole bunch of triangles. And here's something that we know about triangles that you've known for years. Okay? The sum of the measures of the angles of a triangle is 180. So when we talk about a triangle from the previous slide that has 3 sides, we had exactly one triangular region that we could make. And so the sum...
Funny interruption. Conrad and Jose, report to the main office now. Conrad and Jose, report to the main office now.
So if any of you are Conrad or Jose, you probably want to go to the main office. That's what I'm getting. All right. So for the triangle, we had one region, and a triangle has 180 degrees in it. So the number of the degrees of the interior angles is 1, because we had one triangular region, times 180 equals 180 degrees. But if we go back here and we look at this hexagon that we had, there are 4 triangular regions, 1, 2, 3, and 4. And each one of them has 180 degrees in it. So when we talk about a hexagon, we have 4 regions that are triangular, and so the sum of the interior degrees would be 4 times 180. And it goes the same as you might expect for these. For a quadrilateral, we have 2 triangular regions, so 360 degrees inside of it. If we have a pentagon, we have 3 triangular regions, 540 degrees inside of it. Okay? And so that leads us to our first theorem for chapter 6. Well, almost leads it to us. I'm gonna, we'll talk about this slide first. I was thinking we had the next one coming up. So, given polygon A, B, C, D, E, F, G, classify the polygon. Well, that's easy enough. 1 side, 2 sides, 3 sides, 4 sides, 5 sides, 6 sides, 7 sides. Okay? So that makes it a heptagon. Then we're going to, there's usually an N on the end of that. Then we're going to talk about how many triangular regions can you make there. Well, easy enough. We've got, I did it over here, so I'll just pull this out. Okay? Put it right on top. Notice I can make 1, 2, 3, 4, 5 triangular regions there. So what is the sum of all the measures of the interior angles? And what I mean by that, I'll go ahead and say it clearly, is what is the measure of this angle, plus 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 the measure of that angle. Okay? So we have 1, 2, 3, 4, 5 triangular regions, so it's 5 times 180. And that would be 900 degrees, as long as I haven't screwed up my math. Okay? And there it is right there. Good. Moving on. Now here's our theorem. Theorem 8.1, polygon interior angles theorem. This one's super simple. The sum of the measures of the interior angles of a convex, that's the only tricky part there. It has to be convex. A convex n-gon, that means any polygon with n sides, is 180 times n minus 2. See, look at the hexagon that we talked about. We have 6 sides, and there were 4 triangular regions in that. So 180 times 4, and the way we get 4 is just by doing 6 minus 2. So this formula will let us know the measure of the interior angles for any polygon whatsoever. Okay? So if we have a heptagon, you know we're going to have interior angles that add up to 180 times 5, which is 7 minus 2, just like we did in the previous slide. For an octagon, 180 times 8 minus 2, or 6. Okay? Goes on, it goes on, it goes on. The thing is, we can do this for however many we want. Let's say we wanted 1,000 sides to a polygon. Okay? That's going to be an awfully big polygon, or it's going to look a lot like a circle. But we have 1,000 sides, so the measure of the degrees in the inside would be 180 times 1,000 minus 2. So whatever 180 times 998 is, if you want to do that for fun, let me know what it is. I don't care. Okay? This one is yours to do at home on your own, so I'm going to skip it. Notice it says yours number 1. Okay? There's a corollary. Remember, that's something that goes right along with a theorem. It kind of, it's another way of saying the theorem, or something that you can say just by knowing that the theorem is true. So going back to thinking about theorem 8.1, the corollary to the polygon interior angles theorem is that the measures of each interior angle of a regular polygon is 180 times n minus 2 divided by n. Well, that might sound a bit confusing to some of us, so let's just think about what that means. Let's use a regular, how about a regular quadrilateral? That has a special name though, that's called a square. If we have a regular quadrilateral, how many angles, what is the sum of all of the degrees of the angles? That is, as from theorem 8.1, we have 180 times n minus 2, or...
Please pardon the interruption. At this time, the class is in the basement and the 4th floor.
180
Please report to
times
the gymnasium.
2.
Classes in the basement and the 4th floor only. Report to the gymnasium.
Okay. 180 times 2, as we all know, is 360 degrees. 360 degrees is how many, is the number of degrees inside this square. But what we're asking here with the corollary is what are the degrees of each angle? Well, if you have a regular shape, that means you have equal angles. So all you will do is divide this 360 divided by the number of angles. In this case, it's 4. Okay? So we're going to do exactly this formula right here. If we have n, which here was 4, it's 180 times 4 minus 2, which we did right over here, and then divide by n, which we did right over here. Okay? So if you can just remember this formula here, you can tell what any angle is of any regular polygon, even if you have 1,000 sides to it, like we did in the previous slide. Yours number 2, so I'm going to skip it. Yours number 3, so I'm going to skip it. By the way, a stop sign, everybody should know this, draw it out if you don't, has 8 sides. Okay? Theorem 8.2 is the other theorem that we're going to talk about today. The sum of the measures of the exterior angles of a convex polygon is 360. This one's even easier. Okay? First of all, let's review what an exterior angle is. An exterior angle of a polygon is what happens when we extend the line of any side past the vertex. See, the vertex is right here. If I extend this past, then I create 2 different angles. One of them is always 180 degrees. That's not the exterior angle that we're talking about. The other one that's not 180 degrees, that's the one we care about. This is an exterior angle. Okay? Same thing over here. If I extend this one, I have 180 degrees here, which I don't care about. This one right here is the angle I care about. And the same thing, I can extend this one, and 180 degrees, not my exterior angle. The x here, though, is my exterior angle. Okay? There's other ways to do your exterior angles. If I cover this up right here, okay, notice how I had drawn it down for the exterior angle. I can draw it the other way. Instead of extending this line here, I can extend this one here. Notice I have 180 degrees here now, and then on the other side, this becomes my exterior angle. And I can do that, oh, not what I meant to do. I can do that over here and over here as well, okay? I can extend it this way and extend it that way. I forget what they were before, but then, so it was not this one. We can extend it this way, and then the x is no longer our exterior angle. Now our exterior angle is over here, okay? So there are 2 ways to do exterior angles, but the point remains the same. As long as we extend the line and ignore the 180 degree angle, talk about the other one, that's our exterior angle. And it turns out...
Time. Teachers with classes on the 2nd and 3rd floors can come down to the gymnasium. Teachers with classes on the 2nd and 3rd floors come down to the gymnasium.
So clearly I am recording this while they're sending people to the pep rally, in case anybody's wondering. All right, so this one is super simple. Theorem 8.2 just says that no matter how you draw your exterior angles, and no matter what size polygon you have, your exterior angles will always add up to 180 degrees. Or, I'm sorry, 360 degrees. I thought there was something there. I must have erased it. Look at my example up here. I tried to be crazy, but to illustrate a point. If you had a 4,000 gon, okay? That's one with 4,000 sides to it. The exterior angles will all add up to, you guessed it, 360 degrees, okay? Super simple. You remember this. You'll never have to do any thinking. They'll try to trick you by asking you questions like this. The answer is always 360. Corollary to that, though, is that the polygon exterior angle theorem, the measures of each exterior angle of a regular polygon with n sides is 360 divided by n. So, you know how you have all of the angles, I do not want the magic pen for this. All exterior angles equals 360. So each one when you have a regular shape, will be 360 divided by however many sides you have, number of sides, or really number of angles, which is the same thing as the number of sides, okay, which is always going to be n, so you got 360 divided by n. For this case right up here, okay, we have 1, 2, 3, 4, 5, 6 sides, so this is a hexagon. The exterior angles add up to 360 degrees. So each one of them, each one of the exterior angles, because this is regular, will be 360 divided by 6, or commonly known as 60 degrees. Yours number 4 should be a fairly easy question. Yours number 5. And an example that I think finishes us off. Let me just check. Yours number 6. Yeah, that's going to finish us off. So this is the final question that we're going to talk about together. And this is a great question. So pay attention to this one. The measure of each angle of a regular convex polygon is 172 degrees. Find the number of sides of the polygon. Well, what we're going to have to do here is we need to use this formula.
Classes on the first block can now, so classes on the first floor can now report to the gymnasium. Classes on the first floor can now report to the gym.
180 times n minus 2 divided by n. This will help us find n. But how is it going to help us find n? Just like this. Okay, we know that this is the formula for, well, we know that this is the formula for the number of degrees in the interior angles of the figure, and we know that each one of them is going to be 1/n of that. So we take to find the number of degrees in a polygon with, say, 6 sides, we do 180 times 6 minus 2. Now what we're trying to do is find out if this was a hexagon, so 6 minus 2, what's the number of degrees of each? We divide that by 6. So here we don't know how many sides we have, but we do know that each one of these is going to equal 172. So we can solve for this. 180 times n minus 2 divided by n is going to equal 172. Okay? And then we can just do some algebra rules. Okay, I'll do it on this slide. I think the rest of it is on the other slide. But I'll just do it here. First thing we want to do is erase this. Then what we want to do is put my eraser back. Then I want to do n times n to both sides. Okay? What does that do? Well, that crosses those out. So we get 180 times n minus 2 equals 172n. And then what we do is we first want to do our distributive property. Okay, so I'll do 180 times n, 180 times negative 2. I get 180n minus 360 equals 172n. Okay, and then it should be pretty straightforward from there. I don't want n's on both sides, so I'm going to subtract 180n from both sides. Okay. Erase that, extend the page. I get negative 360, don't forget the negative sign, equals negative 8n. And then all I have to do, divide both sides by negative 8. Divide both sides by negative 8. The negatives cancel out. 36 divided by 8 is 4, so 360 divided by 8 is 40, equals, something's clearly wrong. What did I screw up on? I screwed up on something. Times n times n. Well, I'm recording dead air, so let's go to the other page and see if I screwed up on something. Because something seems wrong there. Okay, minus 180. 360 divided by... No, n is 45. Right. Clearly, that's what I did. Okay, going back to this page here. I apologize for that, everybody. Even I'm not perfect. if I could ever scroll down. Okay. 32 divided by 8 is 4, so this is 45. And what question have we actually answered here? We've got 45 equals n. Okay. So let's go back up to our question. Find the number of sides of the polygon. Okay? Number of sides of the polygon would be 45 sides for each angle of a regular convex polygon to be 172 degrees. Okay? So that's a great question. I would expect something like that on an assessment of some sort. Maybe even on a CB. Probably not. All right. Enjoy. Answer your questions. Enjoy the rest of your spring break.